HS, the magnetic field is comes out to be in the AZ direction, whose magnitude is given by this factor. And here J beta over J omega mu is equals to under root epsilon over mu, and this is very important term, and here we replace with this 1 over eta, where eta equals to under root mu over epsilon, and this is called the characteristic impedance or the intrinsic impedance of the medium. So this depend upon the medium, and this is very important quantity, and it will be used later also. For free space, you can find out this value eta naught equals to under root mu naught over epsilon naught, which is it comes out to be 1 over 20 pi. So we have electric field, the direction of, if it is in the direction of y, then magnetic field comes out to be in the direction of z, and they will be a function of x only. Now to obtain the corresponding time varying field or the instantaneous electric and magnetic fields, uh, because this was in the phasor forms, so we can use this equation that real, it will be equal to real part of ESY e to j omega t. You can combine with the time part, and when you solve this, you will get the electric field, instantaneous electric field or the time varying field will be equal to C1 cos omega t minus beta x and plus C2 cos omega t plus beta x. Similarly, we have the time varying magnetic field equals to 1 over eta C1 cos omega t minus beta x minus C2 cos omega t plus beta x. So we have the electric field which is in the direction of uh, y, then this will be h will be the direction of the z. We have ey and z component, and they are function of x and t. Similarly, if we have taken es to be the function or in the direction of z component, then we could obtain ez equals to c1 cos omega t minus beta x, same thing, but now it will be z component, and then we take the h using the Maxwell's third equations, then it will becomes out to be negative. And it will, why it is negative, because we have seen that when applying the Maxwell's equation here, this will have this, you have ax, and now because ESY instead of y it will be the AZ, so EX in cross product with the AZ will give you minus AY. So now that y it will become a negative, so you have a negative here. So we have two equations, electric field and magnetic fields. Now if we see this equation, then this will to be seems to be a function which is moving in the positive x direction as the time passes. Similarly, this is a function which seems to be moving in the negative x direction when time passes. So you can see here, we can visualize that we have already seen this function, that you have f if is x minus vt, then this function fx is moving in this direction. Now instead, if you take the cos omega t minus beta x, so it will be rewritten as cos beta x minus omega t. So at t equals to 0, it will become cos beta x, and this will be somehow, you can see with the x, then this will be some function which is like this nature. Now as if you put up t some finite value which is not 0, then it will be a cos beta x minus omega t seems to be a delayed function of beta x. So what it will be a function which is right shifted by this amount. So here when you plot next time, it will be somehow like this, somehow like this. Similarly, if you further increase the t, then it will again shifted here with the same. So as the time crop passes, time increases, it seems that this function is moving toward the positive x direction. So this is a wave which is moving in the, which seems to be moving in the x direction, propagating in the x direction. Now if we, instead of taking this one, if we take the positive here, if we take the plus one, and you can rewrite this one, so this function seems to be a moving in the left side, that is the negative x direction, that if you have beta x, then if you take plus, it will shift toward the left side. So it will be moving as time increase, it will further shift the left side, and now it will be moving, it seems to be moving in the negative x direction. So same is here, that this is a function, which this is a wave which is moving in the positive x direction, and this is a wave which is moving in the negative x direction, and this is called a forward traveling wave, and this is called the backward traveling wave. Similarly, same case for the hz. So traveling is same, that it also have one part which is moving in the positive x direction and the other is a negative. Only the magnitude, the direction will be changed. The phenomena of moving in that both E and H will be remain same, only their direction and the magnitude will be different, and they will have the same exhibit, phenomena will be same, that is the wave nature will both will have the same. So what we see conclude that the ES and HS are transverse, are perpendicular to each other. Okay, so E, Y and SZ comes out to be perpendicular, and they are called transverse, so we call that transfer electromagnetic fields. So what we call the TEMVs. This is a very important term. And then the assumption of sinusoidal time variation results in the sinusoidal space variation. So we have assumed time harmonics. So what we are getting, that your fields are a sinusoidal in nature. So here uh, we have assumed this phasor form to be a sinusoid, complex sinusoid, and this time variation is also a course. So here in both case, the sinusoidal time variation results in the sinusoid. That is space is also variation in time. If we fix the time, if we fix the t equals to 0 or constant, then it will be a, if you vary with the x, it will be a cosine, it will be a varying sinusoidally. And if we see in the time also at a particular point, if we see, for example, if you are watching a wave at particular point, so this field, this is the x, and you are watching at some particular point, so here this electric field or magnetic field will also vary with time sinusoidally. So it will fix, so it will cos omega t. So the t pass, this will be repeated, it will be increased. The electric field, for example, direction of electric field in this, so initially it will be 0, then increase and go to a peak value, and then it will decrease. So sinusoidally also at particular space point location, with time it also varies sinusoidally. So what it mean by here? So both nature, spatial over time, both are varying sinusoidally. Now, equation 1 to 4 represent the sum of two waves traveling in the opposite direction. Find first one is forward traveling wave, that is called the incident wave, and the other is backward traveling wave, arise due to the some reflection. Okay, I have already explained this one. Now, if C2 becomes 0, this becomes 0, then you have only the forward traveling wave. If C1 is equal to 0, there will be a backward traveling wave only. Generally, C2 may be 0, C1 generally remains non-zero. So if you have only one wave traveling in the positive direction, we have the C1, or we can have both one. So the special case where C2 becomes 0, the only remains here EY is a forward traveling waves. Okay. And if C1 equals to C2, then two traveling waves will combine to form a simple standing wave which does not progress. So they will be exactly cancelling out each other, C1, C2. Here it will be cancelling out, and we will see the standing wave later on the classes, and we will have whole lecture on the standing waves. Right now, just focus on the C2 equals to 0. So let C2 equals to 0, then EY equals to C1 cos omega t minus beta x, and HZ equals to 1 over eta C1 cos omega t minus beta x. So both are traveling in the positive x direction, and the EY is C1. So HZ can be found using the C1, and which is equals to C1 over eta. So what we can have in this case, the Hz, just you can divide by Ey by eta, you will get the Hz. If you know the Ey for the forward traveling wave, just you divide with the eta, with the intrinsic impedance, then you can find the Ez. Or ratio of this component, Ey over Hz equals to eta. Similarly, if we have the Ez, in the case special where the electric field is only direction of the z, then we can have we have from the hy, which is here, and the ratio of this to Ez over hy equals to minus eta. The magnitude will just, if you want to find the magnitude, you can just find the Ez over h by using this formula. And direction you can find with the conventions, how if Ez in z direction, then what will be the y. So now some properties of the wave. So amplitude of the wave C1 has the same unit as E. So this will have the same unit of the electric field, whatever the electric field have. The phase and radiance of the wave depend on time t and the space variable x. It is termed as, the phase is called the omega t minus beta x. So omega is called the angular frequency and beta is called the phase constant, and it is radian per second because it is a t is here, so it will be radian per second. So this is a whole radian term. This is a phase, so radian, and this is t, the radian per second, and beta is a radian per meter. Now we visualize these two individually. So let now that omega t is 0, let we are watching the wave at particular time, that the time is fixed. So what will happen then, the function will become E equals to C1 cos beta. When you plot this cosine function with respect to x, you will get this type of function here, varying sinusoidally in nature, starting from the peak value and decreasing and then negative peak and so on. So when you watch at different point, the electric field here will be maximum, and the magnitude, we are plotting the magnitude. The magnitude is maximum and then it is decreasing, it is 0, and then it is the maximum, but the negative direction will be reverse here, and again so on. It is varying sinusoidally. Now we define the wavelength, where the distance over which the sinusoidal waveform passes through a full cycle. So distance to complete one cycle. So this is have the same peak value. So then again it will complete this cycle and you will reach the same. Now the pattern will be repeated. So this length is called the lambda, or you can say from to here it is a lambda wavelength. Okay. So how to find the this lambda? So if you put x equals to lambda distance, then it will repeat by 2 pi. If you x repeat by lambda distance at lambda, then phase will repeat. So it means if you put L x equal to lambda, then beta x should it comes up to 2 pi. 2 lambda, then 4 pi, and so on. So when you put beta into lambda equals to 2 pi, so lambda is this quantity. Lambda comes out the 2 pi over beta. So wavelength you can find with the phase constant. This is also important relation. You have to remember it. Now, if you're watching at some particular distance, let we want to find the electric field, how it varies with time in the at the origin. For example, you have this x, and you want to see what is how it varies at this point time or this point, how it varies with the electric field. So let's take focus at this origin and see how with time. For example, if it is the ey direction, so ey how this will be constant or it varying with sinusoidally. So here if at x equals to 0, it becomes c1 cos omega t. So again, it will be with time. If we plot with the time here, it will again sinusoid, and we have the time period. Again, we define the time taken to complete one cycle. So here time is passes, and when it reaches again the same phase, same point, then this is called the one time period. So in the time domain, we call the time period, and in the distance, we call the wavelength here. So this is t by 4, t by 2, 3 to the power and t, and so on. So what it seems that if you see in the spatial, when you're standing somewhere and seeing the electric field, so what we can take some another color. So So here when we have this one, so electric field, for example, is the y direction, the electric field will be in this direction, particular t. So when t changes, this magnitude changes sinusoidally, this value will change. So what it will be, for example, somehow maximum at time t equals to 0, and then it will be reduced to some below value and then 0, and then it will change to. So this will oscillate, will seems to be electric field is, if we share with the vector, then vector will have the same direction, that is in the either positive y or negative y, but whose magnitude will vary sinusoidally with time. So it will be increasing and decreasing. So it will be oscillating in nature at particular time c. So it will be somehow like this one electric field. So now t can obtain same fashion as we have obtained the lambda. When the one time period crosses, then this will becomes 2 pi. So omega t equals to 2 pi. So because it comes to the same phase, so equals to t over 2 pi over omega. So you can find the frequency in hertz as omega over 2 pi, or frequency in radians as the 2 pi over t. So this is how you can find the relationship. Now if we visualize both in space and time, what we see, for example, this is a function c1 cos omega t minus beta x. So that one. So we have this omega, this one is the for case when omega t equals to 0. So this is a same wave. Now when suppose that t is changed to certain point where omega t becomes pi by 4. So when this become pi by 4, so it will be shifted by pi by 4. So this wave, what I'm getting here, it will be shifted at point where this phase is pi by 4. This is x. So this phase will be pi by 4 by this one b. So this is a point where the phase becomes, this becomes pi by 4. Similarly, if you again increase a time such that now the phase further increase pi by 2, so it will reaches here. So this now as time passes, the whole point will be shifted by pi by 4. Similarly here pi by 2. So now wave will look like here at t equal to 0. At some t equals to t1, it will be look like this one. Then t equals to this one, and so on. So the wave is shifting towards the right. The wave is seems to be moving in this direction, x direction. It is moving. Okay, so this is how the eyes will perceive the wave in the space. So the electric field is in the space is varying in this way, and they all are moving in this direction with the time passes. At what speed they are moving? So just to find, this is omega t minus beta, or here you can focus. So here if you take the beta common, so it will be x minus omega over v equals in omega over beta into t. Now again, this is the dimension of the distance. So this should be a distance. So now this is time. So if you take out the time from distance, then it will become the speed. So this will become the v. So by this speed, this wave will propagate. That omega equals to v equals to omega or beta. Or you can understand a different way. For example, when this you have the pi by 2 phase here. So at this point, the previously this is the x distance. We are watching the same wave omega t equals to 0, and as you move in the x direction, this is the distance you have traveled, and in this distance the phase is shifted by pi by 2. So pi by 2 is the phase. So x1 is equals to pi by 2 over beta. This is the x1 distance, because beta x equals to beta x1 equals to how much? Now it is shifted to pi by 2. So you can find this distance x1 at this point. Now as the time passes, the wave also reaches at this point. This is shifted by, we can, here you have this have traveled. So t1 equals to this time, this point has reaches to this point here, moving in this one. So we have to perceive that how at what speed this point is moving in this direction. So here it reaches here at this point, the time equals to is such that the phase is again pi by 2. So this is a wave where omega t equals to pi by 2. So this is the time taken to reach this point here to here, such that omega t is equals to pi by 2. So t is equals to time taken is pi by 2 by omega. Now if you want to speed distance upon time, then it will become omega by pi by 2 by beta over pi by 2 by omega, and you will get the same result. So here we have obtained this one. So this velocity is called the phase velocity. So the wave travels this point it perceives to be moving. So what it means that, so so it means that this point, for example, we fix our view on this point or this point. So as the time crosses, this is moving uh, in this direction. So here you at one time it is here, another time it is here, and so on. So if we view this, at what speed is moving in this direction, that is the phase velocity. This is called the view, and how we obtain this is at a speed omega by beta, it is moving in this direction. Another way to understand this phase velocity, because this is very important. So let's focus on certain point P. Only this is the point sum, you have this point P. This point P is moving, or you can say this point, like this is moving some point here. We focus on some phase, a fix on phase. So the point P is a point of constant phase given by this. So what it means that whatever it is moving, so it will have the same phase, because the when the same will phase will be remain same, then you will have the same value of electric field. It means the electric field value should remain as you're moving. This should have the same value in the space. At this point, it is having this value. At this point, it will have the same value. The point which have the same electric field at moving with what speed. So what we can say, the phase is also constant. So for this point, the phase remain constant. This phase remain constant, so that this value remain constant. So we will put equals to omega t minus beta x is equal to constant. So we have to find with what speed this remains same. So we can put up beta equals to omega t, and you can have that v equals to dx by dt, and you will have the omega over beta. In this way, you will also find the phase velocity. How fast is this moving in this? And you can finally v equals to omega over beta. So you can put up omega 2 pi f and beta 2 by over lambda. You will got the important relationship omega. This speed equals to the f into lambda, which you already know in the earlier classes. The same relationship for the free space medium, or any medium which have no free charges and no current density. So this is important term, this phase velocity. So v is equals to omega over beta, and this is f into lambda, but it depends upon the medium only. When you put up beta here, then you will have the v equals to 1 over mu epsilon u. So this phase velocity will depend upon the medium. Okay. So for free space, this is mu naught. Oh, this mu naught we call sometimes mu naught equals to 3 into 10 to the power 8 meter per second. So V is comes out to be this one. When medium is other than the free medium, then you can V in term of mu r and er. So V equals to V naught over under root mu r epsilon r. Now here, what is wavefront? Wavefront, the plane perpendicular direction of propagation. So if you have a wave propagating in this, so if we join the electric, we have electric field, for example, here electric field perpendicular this one, the plane which is perpendicular to this direction, and in which the electric field line is called the wavefront. So it will look like that. The wavefront is moving in this direction. The wavefront, sometimes you will see the wavefronts are moving in this direction. The locus of the point that have the same phase of the field. Okay, so this is a wavefront. So we finish here the discussion of the uniform plane wave for the perfect dielectric or lossless. To visualize this, I have some animations. So let's see with this. So when we have the waves, what will look like? We have for example, wave moving in this direction. So the electric field will have, when ut particular, it is stopped. So we can assume that it is stopped at particular time. So variation the x is will be like this. So you have electric field which is varying sinusoidally in nature here, and you move, and you have a h fields which is perpendicular to this one. So here you can see electric field is perpendicular to this direction. Similarly, the h fields will be here. These are also perpendicular to this one and this one. So they are the transverse electromagnetic fields, TM waves. So we are watching at particular time instant. So this is how you can visualize the EM field at a constant time or a fixed time. Now next, if you visualize this one with time, so what happening there, you have the electric field. For example, this is electric field moving in this direction. So electric field moving. So when you see at particular time, so it will be wave, but you at fixed at some point location in the space, and you watch the electric field. So what you see, electric field is varying sinusoidally in nature here, and magnetic field also varying sinusoidally in nature. Both are perpendicular, and it seems that the way as the time passes, the wave is shifted in this direction. For example, the electric field, so it is moving in this particular, every particular time instant, this wave is shifting toward the positive x direction, the right direction. So it seems that it's moving here. So it looks like the wave, it's moving in this direction. Similarly, h is also moving in this direction. So we both have the same velocity, only the magnitude may differ or the direction is perpendicular to each other. Okay, so this is how you can visualize. Same thing, you can have a different animation also. Here you have electric field and you have a magnetic field moving in this particular direction. And the one you have this one here, you can see again you have electric field and magnetic fields. So electric field is varying sinusoidally, so in time also. And you can say if you stop it, you will see the when you move in the x direction, you will have certain values that, if you pause this, you will have the variation in this. So in the space or the medium which have free from the charges or the current density, in that case the waves will be TEM, that is the transverse electromagnetic waves. The electric and magnetic field will be perpendicular to each other and they are moving in the particular direction. Okay. So this is how the wave moves in the space, EM waves. So we stop it here.